Hello students, welcome to this lecture. In the previous lecture, we are discussing about some exactly solvable models in quantum mechanics, and in part of that discussion, we are looking at the problem of hydrogen atom. In hydrogen atom, we see that we have an electron which moves around the environment of the nucleus. So therefore, the Hamiltonian had one kinetic energy operator corresponding to the nucleus, the kinetic energy operator corresponding to the electron plus the potential energy operator. So here the electron moves around the nucleus and we are expressing the movement of electron in spherical polar coordinate system, where the three coordinates are r, theta and phi. R is the radial part, theta and phi are the angular part. We also discussed that the operator, kinetic energy operator of the electron also has this term is called the Laplacian. The Laplacian already contains the operator L square, which is the angular momentum operator. That is why in the previous class we said that the total eigenfunction of hydrogen atom, that is psi, which will be a function of r, theta and phi, the three coordinates of the spherical polar coordinate system, can be written down as a radial part multiplied by an angular part of the solution. The angular part of the solution is essentially the eigenfunction of the angular momentum operator, because in our hydrogen atoms Hamiltonian, the only operator that had angular dependence was L square operator. So we know its eigenfunction. So therefore, we are using YLM or the spherical harmonics as the angular part of the hydrogen atom solution. That leaves of course the radial part of the solution, and that is what the hydrogen atom solution does. Anyway, we are not going to do the solution, rather we are going to use the results of these exactly solvable models. Now, when we look at the energy of hydrogen atom, we see that the energy E, N, L, M, these are the three quantum numbers. N is the leading quantum number, the principal quantum number, L and M are the trailing quantum numbers, the azimuthal quantum number and the magnetic quantum number respectively. By M value again depends on the value of L, L value depends on the value of N. This is how the flow goes. The energy is given by in terms of a constant, which is minus 13.6 electron volt multiplied by 1 over n square. So that means as we increase the value of n, our energy changes, and the energy levels are shown in this diagram. We also discussed that the negative energy that we get here signifies the stable atom. That means the electron is happily staying in the environment of the nucleus, and when we ionize this electron, the electron becomes a free particle. In that case, that would represent when n is extremely large, n goes to infinite, this energy would turn out to be 0. So that's the situation of ionized state, where the energy levels will be extremely close to each other. So they will have that we will enter the continuous range of energies. But for the stable states, the energy level states are discrete, they are well separated, they take certain values, minus 13.6 electron volt divided and then multiply that with 1 over n square. The other thing that we would discuss here is the degeneracy of these energy levels. So now you see here this energy level corresponds to n equals 1, this is n equals 2, n equals 3 and so on and so forth. While we write down this energy as dependence on n, L, M, the expression that we see has only n dependence, there is no L and M dependence. That is because hydrogen atom is a very special case, it has got only one electron. So therefore, the energy does not depend on L, it only also does not depend on M, it only depends on N. That makes, but for every value of N, we can have n number of L values, because the values of L goes as 0, 1 up to n minus 1. The value of L goes from minus L in the step of 1 to plus L. So for each value of L, we have got 2L plus 1 number of M values. For each value of N, we have got n number of L values, that is from 0 to n minus 1. Now, although for each n, l, m value we can write down the wave function, the energy corresponding to that psi n, l, m shows only n dependence. That is because the hydrogen atom's energy levels are n square fold degenerate. What do I mean? So, when n is 1, the degree of degeneracy is 1, that is 1-fold degenerate or it is non-degenerate. When n is 2, it is 4-fold degenerate, there are 4 states. When n is 3, there are 9 states. So, that means there are 9 different eigenfunctions which correspond to the same eigenvalue E n. So, normally we do not even write L and M dependence because the result does not have L and M dependence. To show the degeneracy of this eigenfunction, I explicitly mentioned n, l, m, but as you see the result, it has only n dependence. When I say n equals 1 has only one eigenfunction, what do I mean? When n is 1, the only allowed value of L is 0, that is 1, n is 1, L is 0, and when L is 0, m is also 0. This is the so called 1s orbital, because it has L is 0, m is 0. When I am considering n equals 2, I see that it is 4-fold degenerate. What do I mean by that? So, when n is 2, I can have L as 0 or 1. So, that is either 2s or 2p. When s is 0, that means L is, when L is 0, that is s orbital, the m value is only 0. So, therefore, that is only one eigenfunction. When L is 1, that is p function, m value can have -1, 0 or +1. In Cartesian sense, we call them px, py, pz. So, this gives rise to 4 different functions. So, all these 2s, 2px, 2py, 2pz orbitals have same energy for hydrogen atom, only for hydrogen atom. It does not apply to all heavier atoms. Similarly, in case of n equals 3, you would see that 3s, the 3 sets of 3p and the 5 set of 3d orbitals, together the 9 orbitals will have same energy. Again, that is for hydrogen atom. For hydrogen atom, the energy levels depend only on principal quantum number. But helium atom, lithium atom, all atoms where more than 1 electrons are there, they depend both, the energy depends on n as well as L quantum number. So, in case of helium atom, 2s and 2px, 2py, 2pz, 2s and 2p orbitals have different energy. 2p orbital has greater energy than 2s orbital. Of course, 2px, 2py, 2pz are same even in case of helium atom and for all other heavier atoms, because unless we have external magnetic field, this degeneracy of px, py, pz are not lifted. That is why we call them as magnetic quantum numbers. But in case of hydrogen atom, life is much simpler. We have simply for n equals for a given principal quantum number, we have n square number of degeneracy or n square number of eigenfunction. Each orbital now can have 2 electrons. So, therefore, we can fill 2n square electron for a given value of n. So, that is how the 2n square rules comes into picture. So, this is about the eigenvalues and the degeneracy. Of course, when we have defined the eigenvalues, we can easily predict the emission spectrum by calculating the difference between the two energy levels, the starting energy level and the final energy level, and that energy separation corresponds to the place where our emission line appears. So, using quantum mechanical results, quantum mechanical model of hydrogen atom, we can now explain the results of hydrogen atom's emission spectrum. Even Bohr's atomic model could do that. But remember, Bohr's atomic model could not explain the hydrogen atom's emission spectrum in the presence of external field. But our model, the quantum mechanical model that we just discussed, this is quantum mechanically accurate. So, therefore, this also explains those cases, for example, the emission spectra in presence of external field or even emission spectra for hydrogen like atoms. So, that means if you have He plus or lithium 2 plus, that means you have ionize all other electrons except for one electron. In those cases also we can explain the emissions, the energy levels of those systems. Now, after discussing the eigenvalues, let us look at the eigenfunctions of the hydrogen atom. The hydrogen atoms eigenfunctions are shown here. So, we see that the eigenfunctions are given as I, n, L, m. They have 3 quantum number dependence. They depend on r, theta, phi, and we are writing that them as multiplication of the radial part and the angular part. The angular part is already we have discussed. They are the eigenfunction of angular momentum operator, the shape of s orbital, shape of p orbital, shape of d orbitals that we are already familiar with, are the results of this spherical harmonics or YLM. So, in this discussion for hydrogen atom solution, we will not bother about the YLM because they are simply the angular part of the solution. What we will be more interested is the new feature that we have encountered is that the radial dependence. Mind you, now where is the radial dependence comes? The radial dependence comes because the electron in this hydrogen atom can now explore entire region, entire length scale, starting from the nucleus to large values, to large separation. So, now how this R dependence affects the wave function, that is represented by this radial part of the solution. The equations are quite scary, but do not worry about them. So, you just like we did for other system, we will also look at the qualitative features arising from these equations. This is R10, that means the first index is n, the second index is L. So, this is 1, n is 1, L is 0, that means this function is for 1s. For 1s orbital, how the radial part of the solution, that is this one, depends on R. Look over here, this is 2 multiplied by z over a to the power raised to the power 3 by 2. Z is the nuclear charge, which is 1 in case of hydrogen atom. So, we do not have to worry about this. A is the Bohr's radius, is again a constant. So, if you express it in atomic units, you know Bohr radius 0.53 angstrom is 1 atomic unit of length. So, therefore, if you express this in atomic units, so this term simply becomes 1 to the power 3 by 2 remains 1. Essentially, what we have is this exponentially decaying function, e to the power minus z r divided by a. So, this 1s orbital radial component of this is shown here. So, this you see that this is simply an exponentially decaying function. The function starts from a finite value at r equals 0, and as you go away from the nucleus, the wave function decays or goes to 0. It has an exponential decay. What it means that if the electron exists in 1s orbital, as you go farther from the nucleus, the probability of finding this electron is 0. But mind you, you may get confused by this finite value of the wave function, the radial part of the wave function at r equals 0, which means that as if the electron is sitting right on top of the nucleus, but will resolve that issue because this is only the radial part of the solution. This is not the probability density, but will resolve that part of the issue, but look at the exponential decay of this function. Now, come to 2s. This is 2s orbital. Now, when you look at this function, let us ignore these constant terms, and every time we have this exponentially decaying function, except for the fact that it is now decaying like e to the power minus r by 2, z is 1, a is 1 in atomic unit, it is decaying e to the power minus z by 2 as opposed to e to the power minus e to the power minus r, as opposed to that it is decaying as e to the power minus r by 2. Apart from this exponentially decaying function, we have got this polynomial. We are not introducing here, but we can actually use the Laguerre polynomials to describe the hydrogen atoms solution. So, this polynomial you can see is a first order polynomial. There will be one value of r at which this polynomial will become 0. So, when this term becomes 0, the wave function would become 0, and that value of r where this particular term becomes 0 would give us the so called radial node. Now, look at the function for the 2s orbital, the radial function of the 2s orbital. You see that this function first decays like this and then comes up here. At this value of r, this function becomes 0. That means it develops a radial node. So 2s electron has the 2s orbital has a node at a given value of at a particular value of r, and what is that value? That value which satisfies this the root of this polynomial. Similarly, when I look at the 2p orbital, so 2, n is 2, l is 1, so this is 2p, it has again a polynomial multiplied by e to the power minus z r divided by 2a. This polynomial is simply r. So now you see at r equals 0, this because the term has r, so at r equals 0 the wave function is 0, and then the lower value of r, the first term dominates. As it picks up as it goes to larger value of r, the exponential decaying term dominates, and then it pulls down the wave function that gives rise to a maximum at one point. When I look at 3p, I see 3p is over here, it has exponentially decaying function multiplied by this polynomial. This polynomial would show that it has got one term r, another term r square. So, it will have two places where this polynomial will be 0. One is the trivial solution when r is 0, the other is the non-trivial solution that is over here when the function becomes 0. So, there are 3p orbital has got one node because we do not consider this one, this point. This is the non-trivial, this is the trivial solution. So, therefore, as we see 1s, 2s has one radial node, 1s has no nodes, 2p has no radial node, 3p has got one radial node, and this way we can describe the radial part of the wave function. While we are discussing about this radial part of this wave function, we always had this thing in mind that the electron is not actually going only along the radial direction, electron is also making an angular movement along theta and phi direction, right. So, to take care of that part, we need to do something that is called the, we need to discuss a very important function, that is the radial distribution function. This radial distribution function is obtained in the following way. Imagine what we actually want to know is to find out the probability of finding this electron at a certain value of r away from the nucleus, does not matter what is the value of theta and phi. It is as if we are trying to calculate the probability distribution in this ring which is separated, which is given by this radius r and radius r plus dr. Once, how do we get that? We can obtain that value if we integrate out the two angular coordinates, that it is the theta and phi, and only retain the radial part of the solution. When we do that, when we integrate out the angular part, we get this 4 pi, and then we have the radial part of the solution, that is r square dr is the volume element in the spherical polar coordinate system corresponding to r, multiplied by this square of this wave function. So, what we are trying to get is the probability distribution of this the hydrogen atom wave function for a fixed for a value between r and r plus dr, no matter what is the value of theta and phi. So, that means we have integrated the theta and phi coordinate. When we do that, the resulting function is called as the radial distribution function. Now, this radial distribution function is a very interesting quantity that gives many useful features about the hydrogen atom problem. So, here what we see is that the radial distribution function for 1s orbital, 2s orbital and 3s orbital. What we see? We see that the radial distribution function of 1s orbital shows a single sharp peak at a small value of r. What does that mean? That means the electron in 1s orbital are more likely to be found closer to the nucleus, and they are found in a very compact region. So, they do not get diffused all over the space. They are found in a very concentrated region of space. That is what 1s radial distribution function says. Look at 2s radial distribution function. What it shows is that it shows a small peak or a small probability at a small value of r. This x axis is the distance between the nucleus and electron. It shows a small peak at a smaller value of r, and larger peak at a large value of r. What does this mean? And in between the two peaks there is a node. So what it indicates? That if the electron is in 2s orbital, we have some probability, that is quite low probability, of finding it close to the nucleus, and then there will be a nodal region where we will never find an electron, and most of the times we are going to find the electron at this value of r. So average distance of the electron when it is in 2s orbital is certainly greater than that when it is in 1s orbital, as the radial distribution function shows. So what has happened is that in case of 2s, the electrons are either found closer to the nucleus or little farther, and in between them there is a node. So that means we know that s orbitals are spherically symmetric. So this shape of 2s orbital shows that we have a small sphere outside and inside, and then there is another sphere outside. In between, the electrons are never found. So the electrons are found either here or there, not in between. So this gives rise to the so-called shell structure. In case of 2s orbital, you would imagine that there is a sphere inside a sphere, and within that electrons are never found, because that is the radial node. Along the radial direction, there is a value of r at which you would never find an electron. When you look at the 3s orbitals radial distribution function, you see there are three places at which the function shows maximum, and there are two places at which it shows node. So in 3s orbital, what happens? The electrons can be found closer to the nucleus, but the probability is very low. It can also be found over here at this value of r, again probability is very low, but most of the times electrons will be found in this range, that is very large value of r. And you see 1s orbital, the radial distribution function of 1s orbital sharply fell. 2s orbital had a slow decay. 3s orbital shows very slow decay. This indicates as we go for higher n value, the electrons are diffused, or they can be found farther and farther from the nucleus. For 1s they are extremely concentrated, 2s they are somewhat, in case of 3s they can be found in a wider range. Now in this picture we see how it depends on n value. Now let us look at how it depends for a given value of n, how it changes from one value of L to another value of L. In case of 3s, you see this is the same function which has got two radial nodes. In case of 3p function, you have got one radial node over here, because mind you, this is the trivial solution, r equals 0. Here you can see that the electron is not found on top of the nucleus, that is obvious. Now in case of 3p, we get one radial node. Mind you, 2p had no radial node, but 3p has one radial node. Again, so if you imagine 3p orbital, so we normally see 2p orbital is a dumbbell shape. So now when I consider 3p orbital, it is a p orbital. It has got an angular node like px or py or pz. So there is a plane along which we will not find the electron, but that is an angular node. So consider 2pz and 3pz. What is the difference? The difference is, in case of 2pz, you have only one angular node, and that is a plane. In case of 3pz, in addition to having that angular node along the plane, we also have a radial node. So that means 3p would appear as a dumbbell within a dumbbell, and in between the two dumbbells there is no electron density. So that is the shape of that is the radial part of the solution. In case of 3d, you see there is only one peak, and because 3D function does not show any radial node. So in this also you can see that how the 3s electron, 3p electron and 3d electrons are diffused, or what is the range of distances that one can find these electrons over there. So one thing that you should notice over here, that you can see 3s electron to be found even for larger distances compared to 3p and 3d. That is because overall probability is 1, and since you have got two nodal structures for 3s orbital, to compensate that the function decays towards a even greater value. In case of 3p, you have got one nodal structure, that is why the function becomes 0 at a certain value, and in case of 3d, you would see the average value is average value of the radial distribution function is smaller than that of 3p and 3s orbital. So, in this way we actually we could learn about the solution of hydrogen atom, the eigenvalues, the degeneracy of the eigenvalues, and the eigenfunctions of this hydrogen atom, which are very popularly known as the orbitals. We know about these orbitals, and we use these orbitals in explaining various chemical features. In fact, since hydrogen atom is the only problem which can be exactly solved, all other heavier atomic system and all other molecular systems mimic the solution that we obtain for the hydrogen atom. So, but those problems, for example, helium atom or hydrogen molecule or any for that matter any other larger molecules, we cannot solve them exactly, and this is where we require approximate methods, and some of those methods will be the topic of our discussion in our future classes. Thank you for your attention.